Hi, my name is Natalie Page, and I'm here to present on the fundamental investigation of hierarchical surface restructuring of electrodes and microelectrode arrays for neurostimulation applications. So this work can be applicable for a variety of biomedical devices used for sensing, recording, and stimulating applications. They could be used for cardiac rhythm management devices, neurostimulation devices, cochlear implants, retinal processes, brain-computer interfaces, and electrophysiology mapping catheters. So we're focused on the electrodes of these devices. We could increase the number of electrodes, but that would increase the size and cause trauma when they're implanted in the body. So we're going to focus on increasing the performance of each electrode. And we'll do this by increasing the electrochemical surface area of the electrode. Typically, these are done by adding thin film coatings with high surface area orientations, but we're going to be focusing on hierarchical surface restructuring as a technology to increase surface area. So hierarchical surface restructuring is a technology that uses ultra-short pulse lasers to roughen a substrate surface. If we look at this first graphic here, we start with just a device or substrate without any type of coating or microstructure. Then we can move on to the microstructure. This could be gained by sandblasting devices just to roughen the surface a bit. We also have nanostructure, where we have much more surface area. These are normally created by thin film coatings like titanium nitride or iridium oxide. And then if we combine the micro and the nanostructures, we have this hierarchical structure, where we see these large microstructures over the surface, but each of those microstructures are made up by nanostructures. And you can see how much this will add to the surface area of the coating. If we look at the SEM images below, we can see a little more specifically what we'll be expecting from the hierarchical structure. In these lower mag resolution SEM images, we see these large rolling microstructures across the surface. There's quite a bit of surface area there, but if we zoom in a little closer onto one of these mounds, we see that they're just made up of many nanostructures. And we see all of the surface area in just this one image, and we see that there's nanostructures all over the entire microstructure, which gives way to a lot of surface area and potentially very high charge storage capacity. Here we have EDS data of the vanadium niobium tantalum mixtures. These were restructured using 200 millimeter per second scan speed. If we look at this first graphic, this first image, we see the vanadium, niobium, tantalum, and platinum elemental maps. If we look at this vanadium, we can see very clearly where the laser ablated away the material from the sample in these black dark areas without the vanadium. Niobium and tantalum look very similar, where their highest intensities match up to the highest intensities of vanadium. We do see some niobium and tantalum in the background. This is likely due to there being less niobium and less tantalum in the sample, so the lower signals look more equal to the signals of higher intensities. We also have the platinum elemental map that shows the highest intensities where the sample has been restructured, which is expected since we're ablating away the coating material and leaving just the substrate in those areas. Below, we also have line scans of the elemental maps, and we can see the green line for platinum has high intensities where the sample has been ablated. The vanadium, niobium, and tantalum coatings show the highest intensities where there is no laser restructuring. To note on this yellow signal for niobium that seems unusually high, there are overlapping intensities for niobium and platinum, so the platinum is probably being miscounted for niobium in these areas. So disregarding that, we see the line scans follow expected trends. So here we have the elemental atomic percent of vanadium, niobium, and tantalum mixtures restructured at various scan speeds. We can see that the vanadium, niobium, and tantalum all follow a similar trend, and we see that at high scan speeds, little to no material is removed. We see it's very linear between 1,000 and 4,400 millimeters per second. Below 1,000 millimeters per second, we see a sharp drop off where a lot of material is ablated very quickly until we get to 30 millimeters per second. We also have the oxygen atomic percent plotted here as well, where we see an almost inverse trend, where we have low scan speeds. We see much higher oxygen percent composition, and when we have much faster scan speeds, we see a much lower oxygen atomic percent. So let's rearrange this in terms of energy per position, and maybe we'll be able to analyze this a little further. To find energy per position, we take the spot size divided by the scan speed multiplied by frequency and pulse energy of the laser. This effectively gives us the energy per position. Here we have plotted the same graph as in the previous slide, except now we are plotting it versus energy per position, and we have it on a logarithmic scale so we can see the data points a little better. The vanadium, niobium, and tantalum at low energy or fast scan speed show little to no material ablated, and as we increase the energy per position, we see that material is removed until there is little to no vanadium, niobium, or tantalum left in the sample. The oxygen at low energy per position shows low oxygen atomic percent, and as we increase that energy, we see that the oxygen atomic percent rises until we see this sort of maxima here. Now this maxima is likely due to the vanadium, niobium, and tantalum, all the reactable materials leaving the surface, so there's less elements for the oxygen to react with, and so perhaps we hit very high energies where the oxygen might be able to react with the platinum. But we see that there's sort of a reactive energy level with the laser and a sort of cleaning level where the oxygen is removed from the surface. In the second graph, we have the same scale, except now we're looking at the material removed or ablated of the single film vanadium, niobium, and tantalum. We have the vanadium in green, and we also see the oxygen percent of the vanadium is the lowest out of all of the samples. We have the niobium in blue and the tantalum in red. So the oxygen follows a similar trend where we see a sort of maxima, and the vanadium, niobium, and tantalum follow the similar trend of being ablated. One thing I would like to note is the tantalum seems to ablate much more quickly than the niobium or the vanadium sample, even though it is the heaviest element. We also perform surface roughness analysis using the white light interferometry over a 450 by 450 micron area. We have a topical graphical map of this area, and we can see the lines from the restructured areas. We also have a profile chart from this data that can show you the depth that the laser is actually ablating into the coating and substrate. So we have plotted the root mean squared height versus the scan speed, and we see that at the lower scan speeds or higher energy per position, we see that the roughness of the surface increases exponentially as we get larger energy per position or slower scan speeds. At higher scan speeds, we see that the surface roughness doesn't really change that much until you get to about 1500 millimeters per second. So we also did XRD of all of the coatings. So here we have XRD of the restructured vanadium. All of the substrate peaks are shown in solid black lines. And we see two grain orientations from this vanadium data. We see vanadium oxide at 111, and we see vanadium 022. So zooming in on the vanadium oxide 111, we see vanadium oxide readily on the non-restructured sample for vanadium. But then once the sample is restructured with 5 microjoules, we see that peak for vanadium oxide disappear. And then the sample restructured at 10 microjoules, we see that vanadium oxide peak start to reappear again. So this would suggest that the coating started with some oxide and at lower energies, we were able to remove the surface oxide. And then with higher energies, we were able to bring that oxide back. We also can look at the vanadium 022 peak that is visible on the original sample that was not restructured. And then this orientation disappears on both restructured samples. This would suggest that there's not enough vanadium material left to observe this peak. So we also have the XRD of restructured niobium. And here we see niobium oxide at 022, niobium at 011, and niobium at 0112. Looking a little closer at the niobium oxide peak, around 30 to 33 degrees, we see that the original sample that was not restructured, we see a very large niobium oxide peak. Similarly to the vanadium XRD, we see that once the sample has been restructured at 5 microjoules, there's no peak for the niobium oxide. Niobium restructured with 10 microjoule, although, has this oxide peak once again, supporting the claim that we can remove oxygen at lower energies and add oxygen at higher energies. We also see the niobium 112 peak on all samples, lowering in intensity after material is ablated away. Moving on to the XRD of tantalum, we have tantalum 002 and tantalum 004. So this tantalum is hexagonal, which is different from the vanadium and niobium, which are cubic. If we think back to the elemental atomic percent versus energy per position, where we saw that tantalum was restructured more quickly than vanadium, this would make sense, seeing that tantalum is hexagonal and it requires less energy to break those bonds. So looking a little closer at the tantalum 002 and the tantalum 004, we see that they both start with relatively small peaks for the tantalum on the original coating, but once they're restructured, they gain intensity for these peaks, suggesting that the laser restructuring is adding energy, enough energy for the tantalum to orient more specifically to the hexagonal orientation. We also have XRD of the restructured vanadium niobium tantalum mixture. So here we only have the vanadium niobium tantalum alloy at 011. This alloy is present originally after deposition, but after the sample has been restructured, we see this peak disappear, suggesting that there is not enough material left to see this orientation. We also have SEM of the vanadium niobium tantalum alloy before restructuring. And we can see that it has cube corners, which supports that we have the vanadium niobium tantalum alloy, which is cubic. So in conclusion, the crystal structure has an influence on the rate of ablation during laser restructuring, since we see hexagonal tantalum restructures more quickly than cubic vanadium and niobium. And also, in addition to forming large areas like in the image, low energy laser restructuring can be used to clean surfaces, where high energy laser restructuring can be used to oxidize surfaces. Thank you for listening to my presentation. If you have any questions, feel free to email me at pagen0@rowan.edu. Thank you.